So rates of change and integration. In other words, when we've got the rate of change, we can integrate and go back to the original quantity that was changing. Work out some formula for that. Okay, 2017. Rate water flowing into a tank. So there it is, d T. Find the amount of water in the tank after 10 seconds. We've been given d T. Now, this is what I was talking about the other day. Yeah, sure, I could just integrate and then I've got a hassle of finding constants, and sometimes you forget. I just find it a lot easier do these sorts of things as a definite integral. So separate out the variables, match the limits that we've been given, and then that eliminates my need to find a constant of integration. So in this case, well, there's only one thing with v, and that is dv. The other side becomes 2 dt on 1 plus t squared. They told me initially the tank is empty. Alright, I was looking for a number. So when t equals 0, v is 0. We want to find what v is when t is 10. So there's the problem to solve. Okay, this one here, I have actually integrated, but remember what I was saying, when you've just got a dv and you're going from 0 to that pronumeral, you could just jump straight and write v for that. That one's okay. The other side, of course, we have to do some integration. That's the log of 1 plus t squared. Technically the log of the absolute value, but of course 1 plus t squared could never be negative, so it doesn't matter with that one. Substituting in, we end up with a log of 101. Imagine that if you say someone, how much water you got? Oh, we got log of 101 litres in there. Well, they did ask for an exact value. 2010, acceleration. It's a trig. Oh, please don't ask us to draw it. Where x is a displacement. Initially the particle is at the origin. Beautiful, we don't have to draw it. Find when the particle first comes to rest. Velocity is what I want to find, isn't it? So I'll write acceleration as dv to t, which will then allow me to separate the variables and solve our problem. Okay, let's pull it all together. Again, there's only one thing with v there, so I've ended up with dv. They told me initially, so when t equals 0, velocity was 1. We want to find the time, so we're trying to find t when velocity is 0. Okay, the subbing in, again, oh well, it's a simple little trig equation to solve eventually. I only need one solution because it said just the first time it comes to it. So I want the first positive solution to this problem, which would be 7 pi and 6 for 2t, which means it's 7 pi and 12 for t. From a couple of years ago. The camera films the motion of a swing in the park. Seats released from rest. Okay, so they've given us some initial conditions. They've given us dv to t. Again, it's a trig one. And we just have to find an expression for displacement. So velocity is dx to t. Separate the variables. X is by itself. Match up our conditions. They told me when t equals 0, the swing was 11.2 meters. We want to find something that links x and t together. This should get us our solution. So, what happens? On the left hand side, we end up with x minus 11.2. The right hand side, let's move the 11.2 over. We have an expression for displacement. A spherical raindrop, that's kind of handy. We've got formulas for spheres. Imagine if it was an actual raindrop. Loses water through evaporation at a rate that depends upon its surface area, and they've given us that rate. dv to t is minus 10 to the negative 4 times its surface area. We have to show that the rate of change of the radius is constant. We want an expression for dr to t. They've given me an expression for dv to t. So now we want to try and link v and r together. There it is, volume. There it is again, volume of the sphere. Oh, surface area, look at that. Hang on. In this case, that's really handy because A is the surface area. That could be useful. So I'm trying to show it's constant. Let's sub that into our formula. Aha! But dv to t was minus 10 to the negative 4a. Our rate was a, but it's the reciprocal of that. The a's cancel. I've ended up with a constant value of minus 10 to the negative 4 for dr to t. So yep, it is a constant rate. But then, how long will it take for the raindrop to evaporate completely? So we now know dr to t is this constant rate. Okay, but it's the radius we need to know what it is initially in order to find out when it's 0. And it didn't come out to be a lovely number. There it is in all its glory. The radius initially is the cube root of 3 times 10 to the negative 6 over 4 pi. I mean, I'm going to do it with calculus. I suppose when you think about it, I didn't need to do it with calculus, because if it's just a constant rate, it's like a linear function, isn't it? I could have done it like a speed equals distance over time type of thing. But anyway, let's do it with the calculus. Separate the variables. Oh well, it just gets dr on one side and t on the other. That one's going from 0 to t, so it just becomes t. This one will end up being... Now, what have I done? Oh, because it's 10 to the 4 subbing in. Bit of number crunching and we get it. 62 seconds. That's how long it's going to take us to evaporate. Okay. I think that's enough for today.